video, I want to share a quick note about using the parallel axis theorem in order to calculate the mass moment of inertia for any arbitrary axis that we might end up needing to rotate a rigid body around. So I'm revisiting my drawing for a cylinder that we looked at before, and we saw that you can draw the equations for this out of a textbook or other lookup reference. The utility of the parallel axis theorem comes when we find ourselves in a situation where we want to or we need to rotate our object around an axis that isn't aligned with one of those that's given in an example. So for example, suppose we for this cylinder we were only able to find equations for mass moment of inertia for rotation about the y-axis, where it's located at the center of the cylinder, rather than rotation about, let's call it the a-axis, which is over here at the end. Now, in that situation, we maybe don't want to have to go derive a new equation. We want to make use of what we already have. Well, the usefulness of the parallel axis theorem is that we can do just that. We can write the equation for the new mass moment of inertia on the basis of something that we know, assuming that we can measure the distance between those two objects. So the variable d here that I'm writing is the perpendicular distance between these two axes of rotation. So what this means for me is that I can compute and come up with the mass moment of inertia around any axis as long as I know the equation for some other axis that is parallel to it, and I can measure or somehow figure out the distance between them. So that's a really useful tool, because now I can move this a-axis to anywhere relative to my cylinder or my rigid body, and I can make this calculation. So doing this, taking this parallel axis theorem, combining it with this idea of superposition, which is that if I have a complex geometry made up of several more simpler shapes, I can just calculate those mass moments of inertia and add them all together in order to get some net or total mass moment of inertia. And that's really useful. With that, we can take relatively simplistic geometry and equations, and we can, come up with stuff for much more complex geometries, much more complex rigid bodies. And that's a really useful tool for us. Thanks.